Do you still firmly believe that the early universe was a peaceful kindergarten where galaxies obediently grew up slowly, according to procedure? Wrong, dead wrong, my brother. The James Webb machine, floating 1 million miles away from us, has just exposed a truth that is much more chaotic. It sees ancient galaxies and massive black holes looming large right when the universe was just learning to toddler walk. Science calls this a cosmological crisis, but to this old man, this is as absurd as walking into a delivery room and seeing a newborn baby, bench pressing 100 kilos. Ready to witness the laws of physics being torn up? Welcome back to Black True. Fasten your seatbelts, my brother. Don't forget, this old man's name is Sengoku. Today, let's leave the worries of food, clothes, and money back on Earth. We are going to cast our gaze 1 million miles away, where a magic eye is hovering in the void, silently observing and laughing in the face of what we humans used to consider truth. Are you ready? Fasten your seatbelts, because this trip is going to turn everything you ever knew about the universe upside down. My friends, we humans often pride ourselves on being smart. We draw up laws, write thick books, and beat our chests saying, "Ah, this is how the universe works." But then a $10 billion machine is launched, and in just a few weeks, it sends back photos that make scientists tear their hair out, wanting to rip up all those old textbooks. That machine is floating 1 million miles away from us, cold and lonely. That is the James Webb Space Telescope. And today, this old man will tell you about how it caught the universe cheating red-handed. Let's talk about James Webb for a bit. This isn't a big spyglass like old Grandpa Hubble. Imagine a tennis court flying through space. That is the size of Webb's sunshield. On top of that is a giant mirror assembled from 18 hexagonal pieces, made of beryllium plated with pure gold. You know, this mirror is so big it couldn't fit inside any rocket. So the engineers had to play a game of jigsaw puzzle, the most expensive style of origami in history. They folded it up neat, stuffed it into the rocket, and launched it on Christmas Day 2021. And then, for 6 solid months, the whole world held its breath. 1,044 parts had to operate perfectly. If just one screw got stuck or one cable didn't deploy, $10 billion would turn into the most expensive piece of space junk of all time. But luckily, Old Man Universe smiled. Everything opened up smoothly, beautiful as a flower blooming in the night. Webb doesn't fly around Earth like Hubble. It hides far away at the Lagrange 2 point, where gravity balances perfectly, allowing it to hide behind Earth to avoid the sun. Its sunshield has a sun protection factor, SPF, of 1 million. Yes, you heard that right. The sunscreen girls use here is only SPF 50, while Webb needs SPF 1 million to keep itself cold enough to reach near absolute zero. Why must it be so cold? To see the faintest light. Infrared. Imagine it like this. Our universe is like a raisin bread expanding in an oven. Everything is running away from each other. When light from the most ancient stars runs toward us, expanding space has stretched its wavelength out. Just like when an ambulance speeds past you, the siren that was high-pitched suddenly becomes deep. Light is the same. It starts as blue or violet, but after a 13 billion-year journey, it gets stretched into red and then into infrared. Grandpa Hubble had poor eyes, only seeing visible light, so to him, the distant universe was a pitch-black night. But with Webb's infrared eyes, it is a dazzling light party that we were never invited to. And the moment Webb opened its eyes, it saw ghosts. Ah, no, more accurately, phantoms from the past. Because light takes time to travel, the farther we look, the more we see the past. Webb sees galaxies from 13 billion years ago. According to our theories, that mess of theories humanity is still proud of. When the universe was just born, about a few 100 million years old, galaxies should have been like newborn babies, tiny, messy, faint, and weak. They needed billions of years to grow, merge, and become magnificent. But no. Webb found a galaxy named Jades. It existed just 290 million years after the Big Bang, meaning when the universe was only 2% of its current age. But Jades isn't a baby. It is blazing bright. It is huge. It has a clear structure. Imagine this to make it easy to understand. You walk into a kindergarten hoping to see babies crawling around, but instead you see a muscle-bound bodybuilder, bearded and rugged, sitting there drinking a protein shake. What would you think? What the hell is this? What is he eating to grow that fast? That is exactly the feeling astronomers have. Jades is too bright, too mature for its age. It challenges every law of development. It's like it's screaming in our faces, "Hey, humans, you guys don't understand anything about how the universe works." Scientists panicked. They checked their machines again. Must be a malfunction or a miscalculation? But no, the numbers stood firm. Jades is over 1,600 light-years wide and is birthing stars at a frantic speed. How can a galaxy grow so fast? Some say, maybe back then stars formed faster. Some say, maybe the Big Bang didn't divide the cake evenly and that spot had more matter. But these are all just guesses. The truth is, Jades and its brothers, yes, Webb found a whole bunch of bodybuilder galaxies like that, are proving that our standard model of the universe is probably dead wrong, or at least seriously flawed. But my friends, the story of these miracle growth galaxies is just the gentle warm-up act. Webb found something much scarier hiding inside them, a thing that breaks the golden ratio of the universe, a monster so greedy that its heart is as heavy as its entire body. What is that thing, and why does it make physicists lose sleep? Excellent. Your curiosity makes this old man very happy. We are stopping in a primordial universe, teeming with galaxies growing fast as the wind. But the strangeness isn't just on the surface. When James Webb looked closely into the internal organs of these galaxies, it found something even more absurd. Take a deep breath. We are about to face the greediest fat guys in cosmic history. My friends, in the modern universe, this old place where we live, there is an unwritten rule, a type of heavenly law that everyone thought was immutable. That is the rule regarding the ratio between the central black hole and the galaxy that contains it. Imagine the galaxy is a giant watermelon. The black hole in the middle should only be a tiny watermelon seed. The exact ratio is 1 to 10,000, meaning for every 10,000 shining suns, there is only allowed to be one sun locked inside the black hole. Our Milky Way follows this law. Neighboring galaxies do too. It is so precise that scientists used it to write the history of cosmic evolution. Ah, black holes and stars grew up together, holding hands through the ages. Sounds romantic, doesn't it? But then James Webb looked at a primordial galaxy when the universe was 570 million years old. It measured the mass of the stars, then measured the mass of the black hole. And the result? The calculator must have wanted to explode. Not 1 in 10,000, but 1 in 10. 1 in 10. Can you visualize the insanity of this number? Imagine your body weighs 60 kilograms. Normally, your heart only weighs about 300 grams, but with that freakish ratio, your heart would weigh 6 kilograms. Or imagine you see a newborn baby lying in a cradle, but it has the heart of an adult elephant beating thumpingly inside its chest. That is exactly what Webb found. An overmassive black hole. I prefer to call it the screen-hogging monster. These black holes don't just sit in the middle, they dominate the whole game. In Webb's photos, they appear as small, fiery red dots. That red color is hot gas swirling into the black hole's mouth, screaming one last time before being swallowed, heated to millions of degrees and outshining the light of the surrounding stars. The million-dollar question here is, why did they get so big so fast? According to old textbooks, old books again, black holes are born when a giant star dies and collapses. Then, that tiny black hole begins eating surrounding gas and dust to grow slowly. It's like trying to get fat by eating 1 grain of rice at a time. It takes a lot of time. But Webb's monsters have had less than 500 million years to develop. Even if they ate enthusiastically at full capacity, mouths open 24/7, it is impossible to go from a tiny star corpse to a giant of millions of solar masses that quickly. Math does not allow it. So there is only one possibility left. A hypothesis that sounds like science fiction, but is gradually being proven by Webb. Direct collapse. Forget the process. Star is born. Star dies. Black hole. This is a shortcut. This is game hacking. Giant clouds of primordial gas, instead of clumping together to form stars due to some special condition, collapsed with a huge crash immediately into a giant black hole. They didn't rise up from poverty. They were born as silver spoon kids, weighing millions of solar masses from the very moment of their birth. They skipped the star phase entirely. One step to becoming the boss. The horror doesn't stop there. These little red dots don't drift aimlessly. They are organized. James Webb discovered they are clustered within what is called the cosmic web. Our universe is like a giant spider web made of dark matter. Galaxies usually lie at the intersections. And these monster black holes? They lie scattered along the silk threads of that web like beads of death strung together. The fact that they are there shows they are the pioneers. They are the first nuclei, the heavy anchors keeping matter gathered together. But here is the tragicomedy. Because they are too greedy, they harm themselves. When a black hole eats, it burps out energy. We call this feedback. This energy is so strong, it blows all the surrounding gas far away. And what is gas? Gas is the ingredient to make stars. So, because the black hole in the middle was too big, too aggressive, it blew away the rice pot of the entire galaxy. It prevented new stars from forming. That is why the galaxies containing them are so tiny. The black hole is like a spoiled brat eating everyone's portion, causing the parents, the host galaxy, to be stunted and unable to grow. You see, the early universe was not peaceful at all. It was a wild place where laws were bent, where monsters were born from the void and suppressed the life of the entire galaxy. But James Webb isn't just good at seeing big, scary things. Its infrared eyes are so sharp they can even see phantoms of light lurking in cosmic dust. Talking about those gluttonous black holes makes this old man thirsty. Do you want to continue the journey to light echoes and ghostly structures in space? I await your command. Excellent. Are you all still awake? I really like patient people, because the secrets of the universe are usually reserved for those who know how to wait. We just left the chaotic banquets of the gluttonous black holes. Now let's let our minds settle a bit. This old man wants to take you to a quieter place, but its beauty is so ghostly it might make you hold your breath. Imagine the phantoms of light. My friends, imagine you are standing in a cave, pitch black as ink. You shout out, "Hello!" A moment later, you hear the echo from the cliff face. That sound tells you the shape of the cave, even though your eyes see nothing. In the universe, light plays a similar game. About 350 years ago, back when people on the ground were still riding horses and shooting muskets, up in the sky, a star in the constellation Cassiopeia, exploded. Boom! A magnificent death. The light from that explosion, let's call it the universe's camera flash, rushed out into space at the speed of light. And now, in the 21st century, that light has just touched clouds of dust floating far, far away. When light hits the dust lights up. James Webb, with its superhuman infrared eye, snapped this moment. We aren't looking at the dead star. It died long ago. We are looking at the dust around it, suddenly lit up by the ghost of the light from that explosion years ago. Astronomers call this a light echo. Sounds poetic, doesn't it? But what Webb saw isn't just poetic, it is also extremely tidy. Before now, we often thought the space between stars, interstellar medium, was like a messy, shapeless fog, like cigarette smoke floating around, with no form at all. But Webb said, dead wrong. When the light echo swept across that dust, it acted like a hospital CT scan machine. It sliced through the dust cloud and revealed the structure inside. Scientists were shocked. They saw wood grains, walls of dust layered upon each other, tight, exquisite, like the skin of an onion. I must emphasize this. This is dust floating freely in the universe, yet it isn't messy at all. It is lined up perfectly straight. These sheet-like structures are about 400 astronomical units wide. Let this old man explain so you can visualize. 1 astronomical unit is the distance from Earth to the Sun. Our entire solar system, out to Neptune, is only about 60 astronomical units wide, radius 30 astronomical units. Meaning these dusty wood grain sheets are several times bigger than our entire home playground. But compared to the whole giant cloud, they are just tiny details, tiny little veins. The question arises, who arranged them so neatly? Who groomed this dust? The answer is an invisible artist we rarely mention: magnetic fields. Recall your physics lesson from middle school. When you sprinkle iron filings on a piece of paper and put a magnet underneath, the filings line up into beautiful curves, right? The universe is the same. The space between stars is crisscrossed with invisible magnetic field lines. Charged dust and gas particles are forced to run along these lines, creating filaments, thin sheets stacked on top of each other. The chaos of gas combined with the order of magnetic fields created a complex 3D architecture that no one had ever seen before. Webb showed us the universe hates sloppiness. Even in the most desolate places, matter follows iron discipline. Stop it, old man. What does stacking dust have to do with me? Is there any brother thinking that? It does, because these dust clouds are star factories. If we understand the internal structure of the cloud, thanks to these wood grains, we will understand how gas moves, how it compresses, and how a new star is conceived. These dust sheets are like highways, guiding gas into gathering points to create stars. Webb isn't just taking pretty pictures. It is redrawing the traffic map of matter in the universe. Thanks to this light echo technique, we don't need to fly there. We just sit and wait for a star to explode, like turning on a flash, and click, snap the structure of the surrounding space. A genius method, right? From monster black holes breaking laws of physics to light phantoms painting wood grain pictures in the void. James Webb is proving that we are like nearsighted people putting on glasses for the first time. Everything is clear, sharp, and far different from imagination. But the journey isn't over yet. The universe doesn't just have formation and quiet structure. It also has the most brutal destruction. All right, resilient astronauts, we have traveled a long road from eat fast, grow fast galaxies to light phantoms. And now we will end this journey with the biggest, most violent explosions in the universe. Prepare your spirits, because what is about to happen in this final part will answer the questions. Was the ancient universe any different from now? And how does one become a giant? My friends, on March 14, 2025, the universe sent us a message, but not a text message. It was a gamma ray. It was a gamma ray burst, flashing for just a few seconds. Telescopes on Earth immediately turned their heads toward it, like news hunters, and they discovered a shocking truth. That beam of light came from a star that died when the universe was only 730 million years old. Picture this: a star 10 times the size of our Sun, living fast, dying young. When it ran out of fuel, its core collapsed with a crash in less than 1 second. The outer layer was blasted out, creating an energy drill piercing through space at nearly the speed of light. That is a supernova. The light from that explosion trudged for 13 billion years to knock on our door. It's like we received a suicide note from prehistoric times. But the most interesting thing lies here. 110 days after the explosion, when the light had faded, Detective James Webb entered the scene. With divine infrared vision capabilities, Webb did something extremely difficult. It separated the light of the explosion from the light of the host galaxy. And when scientists compared this ancient explosion with star explosions in the modern universe today, they fell over backwards. They were identical. In brightness, in spectrum, in how it faded. Everything matched strangely well. Why is it strange? Because back then, the ingredients to make stars were very different from now. The early universe was full of pure, clean hydrogen and helium, while the universe now is much more polluted with all sorts of heavy metals created by previous generations of stars. By logic, that ancient star should have died in a different way. But no, it exploded exactly like its descendants later on. What does this say? It says that the laws of physics are stubborn fellows. Whether 13 billion years ago or now, whether the ingredients are pure or mixed, the death of a giant star still follows a single script. The universe changes, but the rules of the game do not. But the story doesn't end with lonely stars. Webb also found something more terrible, a black hole merger. The system is named ZS7, existing 740 million years after the Big Bang. At first glance, people thought it was just a normal galaxy, but when Webb used a spectrometer to look closely, it saw gas swirling blindly at 2 different locations in the same galaxy. Gas running at hundreds of kilometers per second, heated to millions of degrees. Undeniable signs of being butchered by a black hole. Conclusion: ZS7 has not just one, but 2 supermassive black holes orbiting each other. These 2 monsters are locked in a dance of death. They spiral into each other, getting closer and closer, and their destiny is to collide, to merge into a bigger, scarier black hole. This is the earliest black hole merger ever discovered, and it is the missing puzzle piece to explain the mystery in Part 2. Remember those fat guy, oversized black holes? How did they grow so fast? Here is the answer. Besides eating enthusiastically, direct collapse, they also play the game of big fish eats small fish. They merge with each other. In the early universe, galaxies lay closer together, collided more, so black holes also had more opportunities to combine. You see, with just a few photos and data, James Webb has completely rewritten the history of the universe. We used to think the early universe was a peaceful, slow kindergarten. But Webb has shown it was a fierce battlefield, where galaxies formed in a flash, giant black holes swallowed everything, and stars died with terrifying power. We, tiny humans, are standing before a new ocean of knowledge. Old textbooks are being torn out page by page. And that is the beauty of science. Science is not asserting you are always right, but bravely admitting you were wrong when seeing the new truth. Imagine the system named ZS7. Astronomers just discovered a merger here. Merger sounds too administrative, right? Speaking simply in this old man's language, this is when two galaxies decide to move into the same house. But the interesting thing lies in their hearts. In this ZS7 system, there are two supermassive black holes. They haven't touched each other yet, not yet. They are orbiting each other like two sumo wrestlers circling on the ring. But instead of sweat, they exude energy. Grandpa Einstein, that old man with the frizzy hair everyone knows, predicted this long ago. He said that when two giant objects like black holes orbit each other, they will shake space-time, creating gravitational waves. Imagine the universe is a calm lake surface. Our two black holes are two boulders spinning wildly in the middle of the lake. The ripples spreading out are the gravitational waves. The more they spin, the more energy they lose, the tighter the orbit becomes, spiraling gradually into each other. That is a dance of death. And when they actually crash into each other, boom. Not a sound, the universe has no air, but a gravitational tsunami tearing through space. Do you know what is scary and also amazing? This ZS7 system has a stellar mass only about the size of the Large Magellanic Cloud, a tiny satellite galaxy of ours. But it contains two black holes as big as the final boss black hole at the center of our Milky Way. It's like you walk into a tiny grocery store in the countryside, but the shop owners are Jeff Bezos and Elon Musk sitting there playing chess. These two giants control everything. This proves, right from the primitive beginnings, these black hole monsters played the role of tycoon, shaping the whole universe, not waiting until now. When two galaxies containing these black holes collide, what do you think will happen? Cars crashing? Chaos? Actually, it is more romantic than you think. Stars in a galaxy very rarely crash into each other. Why? Because the distance between them is too vast. Imagine each star is a grain of sand. If you scatter 2 grains of sand 100 kilometers apart, what is the probability of them hitting each other? Almost zero. So when two galaxies pass through each other, the stars just glide past like strangers on a crowded street. But gas clouds are different. They are like thick fogs. When two galaxies collide, the gas clouds slam into each other, getting compressed tightly. And under that terrible pressure, the gas heats up, explodes, and boom! Millions of new stars are born. That is the grandest firework party in the universe. Sometimes I think aliens are definitely much smarter than us, because instead of waging war to grab land, they look up at the sky and see these magnificent scenes. And most importantly, they don't have to go to work on Monday mornings. That must be it. Now, let's talk about something that has given this old man a headache for nights, but feels incredibly satisfying. Light. Astronomers have found a galaxy named Jade's GSZ 14-0. The name sounds like the neighbor's Wi-Fi password, but it is a record holder. This galaxy has a redshift of 14.32. Wait, what the hell is redshift? Let this old man explain in layman's terms. Imagine you draw a blue wave on a balloon that hasn't been inflated. Then you blow the balloon up 15 times bigger. The drawing of that wave will be stretched out, long and drawn out, right? Our universe is exactly like that balloon. It is expanding. Light from the Jade's galaxy left when the universe was only 290 million years old. Back then, the universe was very young and reckless. That light was originally ultraviolet, short wavelength, high energy, like a hyperactive teenager. But it had to run tirelessly for over 13 billion years to reach our James Webb Telescope. Throughout that long journey, the universe expanded, stretching the wavelength of that light beam out. From ultraviolet, blue-violet, it was stretched into infrared, red. A redshift of 14 means the universe has swollen up 15 times since that light beam started its journey. That is why we need the James Webb Telescope. Webb is a giant infrared eye. Normal optical telescopes, which see visible light, would be blind before these galaxies because their light has been dragged all the way to infrared. Think about this for a moment, my brothers. When we look at that faint spot of light from Jades, we aren't seeing it now. We are seeing the past. We are seeing the ghost of a galaxy from the primeval times. The distance to there is not 13.5 billion light years. Because the universe expands, if you could freeze time right now and take a measuring tape, that galaxy has drifted much, much farther than that. It's like you running on a treadmill. You run for 13 billion years, but the machine, space, keeps drifting backward, making the actual distance between you and the starting point terribly far. And to catch that weak, faint light, out of breath, after that long trek, James Webb had to open its pure gold eye wide, exposing for over 70 hours. A respectable patience in exchange for a ticket back to the past. This old man has talked too much, afraid you guys might get indigestion from all the knowledge. We just witnessed the dance of black holes and saw the most ancient light in history. But the story isn't over. The mystery of how fast the universe is expanding is making scientists beat each other's heads open, figuratively only, okay? And the first stars of the universe, the ones never before seen, are gradually revealing themselves. Welcome back to your seats, astronauts. Don't tighten your seatbelts too tight, because in this part, this old man will take you on a cosmic-level speed chase, where numbers are fighting each other clashingly, causing the scientific community to lose sleep and appetite. We have talked about the distant past. Now let's talk about how the universe is swelling up right at this moment. Have you ever wondered how fast the universe is growing? Astronomers use a number to measure it, called the Hubble constant. Imagine the universe is like a giant loaf of raisin bread baking in an oven. As the dough expands, the raisins, representing galaxies, will move away from each other. The faster the bread rises, the quicker the raisins run. The Hubble constant is essentially the rate of expansion of that bread. Currently, this number falls around 70 kilometers per second per megaparsec. Megaparsec sounds formidable, doesn't it? It is actually just a super long ruler, equal to about 3.3 million light years. The rule is very simple. If a galaxy is 1 megaparsec away from us, it is running away at a speed of 70 kilometers per second. If it is 2 megaparsecs away, it runs double that, 140 kilometers per second. The farther away, the faster it runs. Just like when you hate someone, the further you stand from them, the faster you want to run away. Just kidding, but that is the law of the universe. But the trouble starts here. To measure this speed, the scientific community split into two factions using two different methods. And ironically, these two factions produced two results that are totally off from each other. Faction 1. Looking at the childhood ID photo of the universe. They look at the cosmic microwave background, CMB. This is the remnant light left over from the Big Bang explosion, like the heat lingering after the oven is turned off. It shows what the universe looked like when it was just 380,000 years old, meaning it was still in diapers. Based on this newborn photo, they calculate how the universe has grown over time. The result they give: the universe expands at 67.4 kilometers per second per megaparsec. Faction 2. Looking at current streetlights. They don't care about the past. They look at galaxies right near us, searching for supernova explosions. These are stars that explode with extremely stable brightness, like lighthouses or standard 100-watt light bulbs. By measuring their brightness, they know how far away they are and how fast they are running. The result they give: the universe expands at 73 kilometers per second per megaparsec, 67 versus 73. You might say, "Oh, come on, old man Sengoku, a difference of only 6 units. What's the big deal?" Haggling at the market has bigger gaps than that. But no, my brothers, in precision physics, this discrepancy is a disaster. It's like 2 GPS units giving directions. One says you have 67 kilometers left to the destination. The other says 73 kilometers. And both claim they are absolutely correct. This disagreement is called by a very catchy name, the Hubble tension. It has made scientists tear their hair out for decades. Many people hoped maybe it's because the old Hubble telescope is aging and measuring incorrectly. Wait for the superproduct James Webb to go up and see. Surely Webb will resolve this conflict. Everyone thought Webb would find some error in the supernova measurement method and bring the number 73 down closer to 67. Peace would be restored. But life is not a dream. Webb observed the supernovae again with ultra-high definition, eliminating every disturbance, every error that the Hubble telescope might have made. And the result? Webb loudly declared, "My old friend Hubble measured correctly. The speed is indeed 73. So that's it. The hope of machine error has vanished into smoke. The tension is real. The 2 most precise measurement methods of humanity are contradicting each other. When the machines aren't wrong, then what is wrong? Maybe we are wrong. Our understanding of the universe has a gaping hole in it. Let this old man list a few hypotheses that scientists are racking their brains over. We are living in a special village pond. Maybe our Milky Way area lies inside a cosmic void, a place with a lower density of matter than average. Because it is empty, it expands faster than the outside? Sounds reasonable, but measurement data says that's not it. Where we live is as normal as any other place. Dark energy is playing tricks. Dark energy, the mysterious force pushing the universe apart, might not be as stable as we think. Maybe it got stronger over time? Or there is some strange type of energy we don't know about joining the game. New physics? This is the scariest but also the most interesting thing. Maybe Einstein's theory of relativity needs to be revised? Maybe gravity works differently on a massive scale. If the third case is true, then we are standing on the threshold of a new physics revolution. Textbooks will have to be rewritten, and theoretical physicists will have jobs for the next 100 years. The disagreement between 67 and 73 isn't just a number. It is a warning bell that the universe is far more complex, cunning, and elusive than the tiny brain of humanity can grasp. Are your heads spinning with numbers yet? Just stay calm and take a sip of water. The universe doesn't just make it hard for us in the present tense, its past is also full of phantoms that have never revealed themselves. This old man is talking about the first stars, the ancestors of every star, the ones that theory says must exist, but no one has ever seen with their own eyes. They are called Population 3 stars. Sounds like the name of a rock band, doesn't it? We have passed through gluttonous black holes and the universe's speed race. Now, I want you to look down at your hands. Look closely. What do you see? Flesh, blood, and maybe a gold or silver ring. All those things, the carbon in your body, the oxygen you're breathing, the iron in your blood, the gold on your finger, they did not exist when the universe was just born. So where did they come from? The answer lies in the phantoms I am about to tell you about, the great architects that never revealed themselves. Rewind back to the time right after the Big Bang. If you opened a restaurant at that time, your menu would be extremely boring. You only have exactly 3 ingredients: hydrogen, helium, and a tiny bit of lithium. That's it. No carbon to grill meat, no oxygen to breath, no silicon to make computer chips. A pure but tedious universe. The first stars were born from this thin soup. Astronomers call them Population 3 stars. The name sounds scientific, but understand it simply. They are the F1 generation. The strange thing is, we have never seen them. Every star you see in the sky tonight, including the sun, are children, grandchildren, great-grandchildren, generation Y or 2, meaning their bellies are full of metal impurities left by the previous generation. As for the F1 generation, they remain a legend. Why are they so hard to find? Because they lived by the motto of rockers. Live fast, die young. Let this old man explain why. Today, stars form thanks to dust and cold gas collapsing together. Heavy elements, metals, help gas cool down faster, so stars today are often compact, fuel-efficient, like Honda Cub scooters. Our sun burns leisurely for 10 billion years before running out of gas. But population 3 stars are different. Because there were no metals to cool things down, primordial gas clouds were extremely hot and stubborn, resisting gravity. To force this hot gas into a star, you need a massive compressing force. The result? These F1 stars were born with monstrous sizes, 50 to 500 times bigger than our sun. Imagine the sun is a tennis ball, then a population 3 star is a giant yoga ball. And what is the price of being oversized? It is dying early. They burned fuel like a rich guy throwing money out the window. In just a few short million years, a blink of an eye for the universe, they exhausted their energy and exploded. Boom! A horrific supernova. But right in that death, a miracle happened. The nuclear reactor in their bellies managed to forge the first heavy elements: carbon, oxygen, iron. The explosion sprayed these spices into the universe, seeding the later generations of stars, creating planets, and finally creating this old man and all of you. Speaking philosophically, we are the ashes of these dead stars. Sounds both romantic and slightly creepy, right? Webb is playing the role of the famous Detective Conan to find these guys who died 13 billion years ago. How to find them? We can't see individual stars, they are too far, but we can see the light of a whole corporation of population 3 stars gathering together. The clue lies in the spectrum. Normal stars will emit light containing lines of metals. But population 3 stars? Their light must be pure. Only extremely strong hydrogen and helium, no trace of metal. Webb peered into an ancient galaxy named GN-Z11, existing when the universe was only 430 million years old. And guess what? It found very suspicious signs, a strange glowing ratio of hydrogen gas that theoretical models predict is exactly the trace of population 3 stars. Although we dare not confirm 100% yet, scientists are inherently cautious. The hearts of the astronomy world are pounding. We are getting very close to seeing the face of our ancestors. Before these stars, the universe was submerged in darkness. Literally. That phase is called the Cosmic Dark Ages. Back then, the universe was full of neutral hydrogen gas, like a thick fog blocking all light. When the first population 3 stars ignited, they were like giant ultraviolet torches. Their powerful radiation burned away that fog, a process called ionization, tearing apart gas atoms, making the universe transparent. Without them, the universe would forever be a dark, murky, and gloomy place. They flipped the light switch for this entire universe. A magnificent job, right? This old man just told you about the silent heroes who created the heavens and earth. But while looking for these heroes, the Webb telescope accidentally stumbled upon another freakish thing. This thing is not in the textbooks. Crimson points of light, tiny but containing terrifying power, challenging all our understanding of black holes and galaxies. Scientists call them by a name that sounds very cute but is full of mystery: little red dots. Welcome the most patient brothers who have traveled with this old man to the final leg of this journey. If in the previous part we looked for silent heroes, population 3 stars, then in this part we will encounter the weirdest guys, the ones making the scientific community tear their hair out and overturn every book. The universe always likes to play hide and seek, and the newest surprise gift that the James Webb Telescope, Webb, sent back is things that are tiny, blood red, and full of defiance. When Webb looked deep into the early universe, about 1 to 2 billion years after the Big Bang, scientists expected to see beautiful spiral galaxies or messy clouds. But no, what hit their eyes was a series of crimson points of light, tiny and extremely dense. They call them little red dots. The name sounds cute like the name of a children's song, but don't let it fool you. Why are they red? Not because they are shy. This red color comes from hot gas around a central black hole, or because dense dust blocks blue light, only letting red light escape, like the sun at sunset. What made this old man and colleagues fall over backwards is their quantity. They are as numerous as mushrooms after rain. No one thought the universe back then contained so many objects that were red and dense like that. It's like you walk into a kindergarten and see nothing but babies with the strength of bodybuilders. The real headache began when scientists analyzed the light spectrum of these red dots. Usually, galaxies are divided into two clear factions. The black hole faction, AGN. Gas around the black hole spins extremely fast, thousands of kilometers per second, creating broad spectral lines. The star formation faction. Gas moves slowly, more gently, creating narrow spectral lines. But what about these little red dots? They have both. They are like a guy wearing a suit to a meeting, black hole sign, while also wearing swim shorts, star formation sign, at the same time. The broad lines betray that at the center is a black hole monster devouring matter frantically. The narrow lines whisper that around it, stars are being born in droves. Furthermore, all this chaos is compressed into a super tiny space. Our Milky Way is 100,000 light-years wide. And these red dots? They package that huge energy source into a region only under 1,000 light-years wide. 100 times smaller, but blazing brilliantly. This is truly the definition of small but mighty. So what on earth are they? The astronomy world is arguing loudly and proposing three main scenarios. Hypothesis 1. Shy quasars. Maybe these are normal supermassive black holes, but covered by a layer of dust that is too thick. The dust blocks all the dazzling light, leaving only infrared red, like a car headlight covered by a thick blanket. Hypothesis 2. The puberty phase of galaxies. This is the hypothesis this old man likes best. Maybe we are catching galaxies in a brief transition phase. The central black hole just flipped the switch and started eating frantically, while the galaxy is still birthing stars continuously. A chaotic vitality before the black hole becomes too big and suppresses everything. Hypothesis 3. The cosmic Webb's party. Maybe these red dots lie at special intersections of the cosmic web, where gas rushes in too much, triggering both the black hole and star creation at the same time. Recently, when analyzing 7 of these little red dots carefully, scientists discovered a shocking truth. The black hole here is too big compared to the galaxy containing it. In the modern universe, a black hole usually only accounts for about 0.1% of the mass of the entire galaxy. It's like the seed of an avocado, just small. But in the little red dots, the black hole accounts for up to 10% to 20% of the stellar mass. Imagine meeting a 10-year-old child, but his head is the size of a giant's head. This overturns all theories. It suggests that, in the early universe, maybe black holes formed and grew up first, then the galaxy developed around it later. or black holes have a way to cheat to grow faster than the allowed speed. People often say, "Can't see the forest for the trees." But in the universe, sometimes we see the stars, trees, but forget that they are lying in a giant forest, connected by invisible roots. Ready? Start your thinking engines. When you look up at the night sky, what do you see? Scattered spots of light on a pitch-black background, right? It looks random, like someone accidentally spilled a jar of salt onto a black kitchen table. But no, oh good brothers, the universe is not messy like your room. Just kidding, I know you guys are very tidy. In reality, the universe is organized extremely tightly. It is not homogeneous. Matter is not spread evenly like butter spread on bread. Under the molding hand of a builder named gravity, matter clumps together, creating a grand structure that astronomers call the cosmic web. Imagine you are sitting on a plane looking down at Earth at night. You will see brilliant city lights. Those are galaxies, connected to each other by bright highways. Those are filaments of matter. And between those cities are giant dark regions of fields or oceans. In the universe, those dark regions are called voids. Those are giant bubbles, lonely, cold, and containing extremely few galaxies. As for galaxies, stars, and even us, we are crowding to live along those grand highways. At the intersections where roads cross, we have galaxy clusters, the busiest supercities of the universe. Where did this web come from? Did someone draw it? The story begins at the dawn of time, right after the Great Big Bang. Back then, the universe was like a bowl of hot, thin porridge. But this porridge was not completely smooth. It had tiny lumps, tiny density fluctuations. Any region that was a little denser, like a lump of flour in porridge, it would have stronger gravity. And so it started sucking everything around it towards itself. The rich, dense regions got richer, sucked more matter. The poor, thin regions got poorer, had all matter sucked away. Over billions of years, this rich get richer process turned those tiny initial ripples into the giant web we see today. But old man Sengoku, how do you know about the old days? You didn't live since the Big Bang, did you? True, this old man is old, but not that old. We know thanks to the golden boy of the astronomy village, the James Webb Space Telescope. Webb isn't just fancy binoculars, it is a literal time machine. Light needs time to travel. When you see light from a galaxy 13 billion light years away, it means you are seeing its image when it was still wearing diapers, when the universe was just a toddler. Webb mapped galaxies when the universe was less than 2 billion years old. And guess what? That cosmic web was already there. Even though the filaments were short, faint, and the galaxy cities were just pouring their foundations, the basic architecture was established. Astronomers measured what is called redshift. Quick explanation, ELIF. Imagine the universe like a piece of rubber being stretched out. Light passing through the universe is also stretched along with it. Light waves that are stretched long will turn red. The farther the galaxy, the redder the light. Measuring this redness, we know where it is and how far away. Results show that even when the universe was less than 1 billion years old, redshift equals 8, galaxies had already gathered in gangs along the filaments of matter. They did not wander aimlessly at all. This is the most interesting part, and also the part that hurts the human ego the most. What we see, stars, galaxies, gas, and even the body of old man Sengoku here, is just the tip of the iceberg. We are just glittering dust particles decorating an invisible Christmas tree. That Christmas tree, the true skeleton of the cosmic web, is made of dark matter. It makes up 85% of the total matter in the universe. It doesn't glow, doesn't reflect light. It ignores all our observation. It is like a supreme ninja. We only know it exists because we see galaxies being sucked together by some invisible, extremely large gravitational force. Dark matter is the silent architect. It created the frame first. Galaxies, normal matter, are just the freeloaders, following wherever there is the most dark matter to form. The Webb telescope cannot see dark matter directly. How do you see an invisible ninja in the dark? But by mapping glowing galaxies, Webb indirectly drew the map of dark matter. Like seeing car headlights moving in the dark on a mountain, you know for sure there must be a road there, even if you don't see the asphalt surface. Our scientists love playing SimCity with the universe. They load data about dark matter and gravity into supercomputers and run simulations to see how the universe will grow. And good news, on a large scale, looking at the whole, computer simulations and Webb's actual observations match surprisingly well. We understood the basic rules of the game correctly. But there is always a but. On a smaller scale, things start to get messy. Computers predict there will be many small galaxies here, few there. But what Webb actually sees is different. What does this mean? It means the galaxy formation process is much more complicated than we thought. Maybe us humans are still missing a few pages in this universe's instruction manual. Fun fact, you know, the location of a galaxy in this Webb determines its fate. If you are a galaxy born at an intersection, galaxy cluster, your life will be full of storms. You will collide, merge constantly, be torn apart, like living in downtown New York or Tokyo during rush hour. If you are born in a void, you will have a quiet, lonely life, evolving slowly, like a hermit living on a mountain peak. And Webb discovered those little red dots, gathering in very specific areas, not too crowded, but not too empty. Perhaps those are the ideal suburbs for black holes to thrive most strongly. In the previous part, we saw that the cosmic web was built properly, but the first residents living in it behaved extremely strangely. Ready? Let's fly. In the current universe, let's call it the local universe to be fancy, galaxies live quite comfortably. Stellar density, meaning the number of stars stuffed into a space, is at a breathable level, like you living in a spacious garden villa. But when the Webb telescope looked into the past, at the time of the early universe, it discovered a shocking truth. Galaxies back then were compressed to the point of suffocation. Imagine it like this. Take all the stars of a large current galaxy, then stuff them all into a box 1,000 times smaller. That is the state of ancient galaxies. This old man calls this bus rush hour syndrome. Stars crowded together in narrow spaces. There, collisions between stars, something extremely rare in our era, could happen as often as daily meals. You step out into the alley and bump into a neighbor immediately. This is when things become headache-inducing. According to normal logic, if you want something to get bigger, you have to add more meat to it, right? Want the cake to get bigger, you have to add flour. But these galaxies play a paradoxical game. They start from a small and dense state, then evolve into big and diffuse, like galaxies today. The million-dollar question is, what the hell puffed them up? How did they expand their size 1,000 times without adding too much mass? This is the opposite of most previous predictions. We still thought galaxies grew by eating, merging with other galaxies. But eating a lot should make you fat or gain mass, so why get diluted? Astronomers have had to rack their brains and come up with a few hypotheses that sound very sci-fi, but are extremely reasonable. Culprit number 1. Ghostly collisions, mergers. When two galaxies crash into each other, do you think they go boom like two trucks crashing? No. Stars, even though crowded, are still very small compared to the void of space. When two galaxies merge, their stars pass through each other like two ghost armies. However, gravity will do the work. It scrambles everything, pushing stars further out. Result, the newly formed galaxy will be bigger, bulkier, but the average density decreases. Like mixing two handfuls of cotton balls and fluffing them up, it becomes a big fluffy pile, but very light. Culprit number 2, weight loss, wind, feedback. Early galaxies were very fierce. Supernova explosions, dead stars, and gluttonous black holes constantly spewed out terrible streams of energy. This old man calls this galactic-scale wind. These winds are so strong they blow gas out of the galaxy center. When matter, gas, is blown away, gravity in the center weakens. The stars that were being held tight suddenly feel a loose grip, so they drift further out, orbits expanding. The galaxy naturally puffs out like a balloon being let loose. Culprit number 3, the dark matter ghost, him again. Every galaxy lies inside a giant dark matter cocoon. When this cocoon changes shape or merges, it changes the gravitational playing field, causing the stars inside to also move further out to adapt. Before Webb, many scientists said, "Stop it, you generals," probably because the Hubble telescope doesn't see clearly, seeing it blurry, so thought it was small and dense. Must be an optical illusion. That was a reasonable argument. Measuring the size of a faint smear of light 13 billion light-years away is as hard as measuring the waistline of a mosquito flying in Hanoi while you are sitting in Saigon. But Webb, with its sharp infrared eyes, crushed all doubts. It confirmed, this is real. Webb looked through the dust, resolved every little detail, and affirmed, early galaxies were truly dense, compressed lumps. Not a camera error, but due to their structure being truly different. Part of the reason is also that young galaxies contain a lot of gas, and gas is easier to compress than stars. When a galaxy ages, gas turns into stars. Stars are stubborn, refusing to compress anymore. So the overall density naturally decreases. We just witnessed a strange puberty of galaxies. From tiny, tough, dense children, they went through collisions, cosmic winds, to then puff up into relaxed light giants like our Milky Way today. Understanding this process, we finally understand why our home looks like this and not like a cramped sardine can. But wait, do you think the strangeness stops at density? Big mistake. Webb also found something scarier, a galaxy named Jades. According to theory, it should be a faint spot about to go out, but in reality, it is blazing brightly in an absurd way, challenging every law we used to trust. How bright is it, and why does it break the game like that? Take a deep breath now. Let's move on. My friends, in physics, there are very basic laws. For example, the farther you go, the weaker the light gets. If you shine a flashlight on your face, it's blinding, but if you hold that flashlight and stand on top of Mount Everest shining it down, I defy anyone to see it. The universe is the same. Light from distant galaxies must travel for billions of light years, getting stretched by the expanding universe, redshift getting diluted. Theoretically, galaxies at the edge of the universe should be as dim as a firefly about to run out of battery. But then the Webb telescope appeared and found JADES. It lies over 13 billion light-years away from us. It should be totally dim, even invisible. But no, JADES is blazing bright. It is so bright that Webb could detect it even if it were 10 times dimmer than it currently is. And JADES is not alone. Webb found countless such lighthouses everywhere in the primordial universe. This is like looking up at the night sky and seeing thousands of stars shining like car headlights, even though they are incredibly far away. Cosmologists had to exclaim, "What the hell is going on here? Are the textbooks all wrong?" Why is it so bright? Simple. Star formation. The light of a galaxy mainly comes from young, hot, and energetic stars. The more stars a galaxy births, the brighter it is. Let's compare the Milky Way, our home. A calm, old man, only birthing about 1 to 2 new stars per year, equivalent to the mass of the Sun. Very lazy. Jades, the rebel. An energetic, young man, birthing dozens, even hundreds of new stars every year. Jades' working speed is dozens of times that of the Milky Way, even though its size is much smaller. It's like a tiny factory, but operating at full capacity 24/7, with the furnace burning continuously. And speaking of size, Jades is also a mystery. It is about 1,600 light-years wide. Sounds big, but compared to the Milky Way, 100,000 light-years, it is just a grain of sand. However, given its young age, this size is too big. It grew fast like St. Jiang. Why were galaxies back then so fertile and brilliant? Old man Sengoku has compiled a few reasons from scientists here. First, free gas buffet. To create stars, you need fuel, which is gas. The early universe was like a giant buffet party where pristine hydrogen and helium gas flooded everywhere. Galaxies just shoveled it in, continuously loading fuel to cast stars. No worry about fuel shortage like the old galaxies of today. Second, no sunglasses, dust. In the modern universe, there is a lot of cosmic dust created from the corpses of dead stars. This dust is like a fog, blocking and absorbing some ultraviolet light. But in the early universe, everything was still very clean, little dust. Light from young stars just shot straight into space, unhindered by anyone, so they look much brighter. Third, weak police, weak feedback. Normally, when too many stars form, black holes or supernova explosions will become active, creating winds that blow the gas away, preventing further star birth, like police quelling a riot. But in this era, black holes were still small. Supernovae were not yet numerous. No one forbade it, so the star party just went on crazily. Scientists are still not satisfied. They suspect there is some hidden twist. The caught-in-the-moment hypothesis. Starburst? Maybe Jades isn't bright like that forever. Maybe we accidentally saw it right when it was peaking, a brief burst of star explosion lasting a few tens of millions of years, extremely short compared to the age of the universe, like taking a picture of fireworks right when they explode. The giant monster hypothesis, top-heavy IMF. This is the one this old man likes most. Today, the universe mainly creates small and medium stars, like the Sun. But who knows, maybe back in the day, the universe liked to play big, prioritizing the creation of only giant monsters weighing hundreds of times the Sun? These stars burn much more terribly bright. If this is true, we have to rewrite the entire evolutionary history of stars. What does this mean? Discovering these brilliant galaxies isn't just for fun viewing. It solves a big problem. Rionization. The universe once had a dark, murky era. It was these brilliant galaxies that released a huge amount of radiation, tearing apart that fog and lighting up the universe faster than we thought. They were the pioneering torches breaking the darkness. We have gone from macrostructure, cosmic web, to the strangeness of the distant past, Jades. But do you know? Right next door to our house at the nearest neighboring star system, Webb has also just found something shocking. No need to look 13 billion light-years away anymore. Let's look right at the neighbor's house. Is someone living there? Now, turn off the hyperspeed engines. We will glide back to right next door to our house. Don't think only distant places have strange things. Even our neighbor's house is hiding earth-shattering secrets. You surely all know Alpha Centauri, right? It is the star system closest to us, only over 4 light-years away, a walking distance of a few tens of thousands of years. This star system has 3 members. Proxima Centauri, the tiny youngest brother, red dwarf, where we found the planet Proxima b that might have life. Alpha Centauri A and B, 2 big brothers, bright and looking exactly like our sun. The problem lies here. These 2 big brothers are too bright. Searching for a planet orbiting them is like trying to see a firefly flying right next to a lighthouse. Ground-based telescopes all gave up, but the Webb telescope said, "Hold my beer." Using mid-infrared tools, astronomers created a special pair of sunglasses to block out the blinding light of the parent star Alpha Centauri A. And bingo! They saw a faint spot of light. That spot of light lies in an extremely beautiful location, the habitable zone, where liquid water can exist. But don't celebrate too soon. Data shows this is likely a giant gas planet like Jupiter or Saturn, not a rocky planet like Earth, meaning you can't land a spaceship there for a walk because there is no solid surface to walk on. So that's pretty boring, right? Not at all. Remember our Jupiter. It is gas, but its moons, like Europa or Enceladus, are rock and ice, have underground oceans, and are the most promising places to search for life. If this gas planet over at Alpha Centauri A exists, it might carry large rocky moons. A moon located in the habitable zone? That is the script of the movie Avatar with the planet Pandora. You get my drift? A livable world right next to us? Of course, this old man must correct. This is just a tentative discovery. More time is needed to confirm 100%. But just the fact that Webb saw it is already a miracle. Take your eyes off the stars for a bit. Look into the black space between them. We often call it a vacuum, but actually it isn't as empty as this old man's wallet at the end of the month. The space between stars, interstellar medium, is full of gas and dust. Before, we thought it was like a dim, chaotic fog. But Webb once again made the scientific community fall over backwards when observing the light echo phenomenon in the constellation Cassiopeia. Webb looked through the dust layer and saw that the gas and dust there don't float messily. They are arranged into sheet structures stacked on top of each other extremely neatly. Imagine it like layers of a meal crepe cake or thin sheets of silk stacked on top of each other. Who arranged them so neatly? The main culprit is magnetic fields. In space, gas is often ionized, loses electric charge, so they are guided by magnetic fields. Magnetic field lines are like invisible rails, forcing matter to run along a framework, creating fragile and exquisite fiber sheets. Why is this important? Because it is exactly at the places where these silk sheets intersect or compress that new stars will be born. Understanding this structure, we understand how a galaxy gives birth to stars. This old man wants to ask you a question. Have you ever tried measuring the length of your bedroom? Easy, right? Just a tape measure and you're done. But what if I asked you to measure the distance from Earth to a star far, far away out there? We can't hold one end of a tape measure, then ask an alien guy to hold the other end and pull it tight. The universe doesn't work like that. The universe is so vast, it makes the tiny brains of us humans smoke. But humans, though tiny, are very curious and stubborn. We have devised all sorts of ways to measure the universe. And today, this old man will tell you about how the James Webb Telescope, humanity's magic eye, is rewriting the textbook on cosmic distances. First, let's talk about the neighbor stars. With these nearby buddies, astronomers use a trick called parallax. The name sounds dangerous, but its principle is exactly like this child's game. Hold a finger up in front of your face. Close your left eye, open your right eye. Then switch. Close your right eye, open your left eye. What do you see? The finger seems to jump back and forth relative to the wall behind, right? In the universe, our Earth orbits the Sun. When we observe a star in January, then look at it again in June, meaning on the opposite side of the orbit, that star will jump position slightly relative to the distant background sky. Measure that jump, apply a bit of middle school triangle math, and you get the distance. But life is not a dream. This winking trick only works for neighbors close to home. With objects farther away, they stand still, not moving at all. At this point, the triangle ruler is useless. We need a heavier weapon, standard candles. Imagine you are standing in pitch-black darkness. You see a street lamp. If it is bright, you know it is near. If it is just a faint spot of light, you know it is far. That is because you know the actual brightness of that light bulb is so many watts. In the universe, there are also light bulbs like that. First are the Cepheid variable stars, guys. These are very interesting stars. They pulsate like a beating heart. Brighten, dim, then brighten again in an extremely regular cycle. Astronomers discovered a beautiful rule. The slower the star beats, the greater its actual brightness. That's it. Just time the beat. This old man knows its true brightness immediately. Compare it with the dim brightness seen from Earth, and calculate right away how far it is. But the universe is vast. There are places so far that Cepheid stars cannot be seen. At this point, we need an explosion. A really big explosion. That is a Type 1a supernova. Just imagine it like this. There is a white dwarf, the corpse of a star, but it is extremely greedy. He keeps sucking matter from the star next to him. He eats forever until he reaches exactly a specific weight limit, then boom! He explodes. Because the weight limit at explosion is fixed, the brightness of this explosion is always the same, no matter where. It's like buying exactly one type of firework. Whether you light it in Hanoi or New York, its brightness is the same. Seeing that explosion, we know the distance immediately. And this is when our main character appears, the James Webb Telescope. Previously, people often argued about the accuracy of these rulers, but Webb, with its sharp infrared eyes, has verified new, extremely cool methods. Webb looks at old stars expanding, called red giants. When these guys get old, they gradually brighten until they reach a certain brightness ceiling and then stop, unable to get brighter. This ceiling is called the tip of the red giant branch. It's like everyone walking through a door has to duck to the same height. Webb sees this ceiling clearly in galaxies tens of millions of light years away from us. Furthermore, Webb also uses carbon stars, stars with atmospheres full of soot. Sounds dirty, but in Webb's infrared eyes, they have extremely distinctive colors and brightness, becoming a brand new ruler. Why is this old man rambling on about these rulers? Because it resolves a loud argument in the astronomy world called the Hubble tension. The story goes like this. Scientists want to know how fast the universe is expanding, Hubble constant. But the trouble is, measuring one way gives one number, measuring another way gives a different number, like two GPS units pointing two different ways. One side uses supernovae, saying it's fast. One side uses Big Bang remnants, saying it's slower. Physicists look at each other confused. Is our physics knowledge totally messed up? But James Webb stepped in like a fair judge. A recent study used Webb to measure the distance to 10 galaxies using all three methods at the same time: Cepheid stars, red giants, and carbon stars. What was the result? All three rulers gave the same number. The Hubble constant is about 70 kilometers per second per megaparsec. What does this mean? It means Webb isn't wrong. Our telescope measures extremely accurately. That tension might not be as serious as we thought, or the universe is playing a more complex game that we don't fully understand yet. But most importantly, it affirms that we have reliable tools in hand to draw the map of the universe. But my friends, measuring distance is just the warm-up act. Webb isn't just an expensive ruler, it is a time machine, taking us back to the past to witness the real monsters shaping this universe. This old man is talking about the greediest, darkest mouths. Supermassive black holes. And believe me, they don't just know how to eat, they also know how to spit out things much more terrible. In the previous part, this old man said black holes don't just know how to eat. This sounds contradictory, right? We often hear rumors that black holes are the greediest monsters in the universe, swallowing everything, including light. A great miser, only knowing in but not knowing out. But in truth, my friends, black holes are very messy and sloppy eaters. Imagine trying to pour a large bucket of water into a tiny funnel in a split second. What happens? The water won't drain down in time, it will swirl blindly, splashing out, right? Black holes are the same. When cosmic gas and dust are sucked into the event horizon, they don't fall straight down immediately. They spiral frantically, rubbing against each other. This friction is so terrible, it heats the gas stream to millions of degrees. Matter at this point is no longer normal gas. It screams and glows brilliantly across all energy spectra. And this is when the miracle, or more accurately, disaster, happens. The pressure from this hot radiation is so strong it pushes gas back out. Instead of being swallowed, a huge amount of matter is shot far away from the black hole at terrifying speeds, thousands of kilometers per second. This old man calls this the wind of the black hole, but don't mistake it for the northeast monsoon in Hanoi. These winds carry destructive energy. They sweep through the entire host galaxy. Imagine a galaxy like a bustling construction site where gas and dust are mortar and bricks to build new stars. The black hole in the middle is like a cranky foreman. When he gets angry, meaning eats too full and spews energy out, he takes a high-power blower, blowing all the bricks and mortar out of the construction site. What is the result? No more gas, no more bricks and mortar. The galaxy cannot create new stars anymore. The development of the galaxy is completely halted. The scientific community calls this process by a very technical word, feedback. As for this old man, I call it simply foreman on strike. Thanks to James Webb's sharp infrared eyes, for the first time we saw this foreman running wild, right in the early universe. Webb caught galaxies with supermassive black holes operating extremely powerfully. Spectral data shows gas being pushed out from the center at velocities up to 3,000 kilometers per second. This speed is so fast it overcomes the galaxy's gravity. The gas flies away and never returns. This decodes a mystery that has given astronomers headaches for so long. Why in the early universe were there black holes absurdly large compared to the galaxy containing them? It's like seeing a newborn baby, galaxy, but with a head as big as an adult, black hole. Looks very disproportionate. But thanks to Webb, the story has been clarified. In the early stage, the black hole developed first. It ate voraciously, grew fast as the wind, and precisely because it ate too much, it created extremely strong energy winds, blowing away surrounding gas, preventing the galaxy from forming stars to grow. The black hole is like a greedy child, eating all the nutrition, causing the body, galaxy, to be stunted and malnourished. But every party must end. At some point, the black hole eats all the surrounding gas. It gets hungry, the emitted energy decreases, the winds weaken. At this time, gas from outside has a chance to cool down, settle, and start clumping to form stars. The galaxy begins a late puberty stage, building up its stellar mass. It takes hundreds of millions, even billions of years later, for the galaxy to grow big enough to be a perfect match with the black hole at the center. That is why in the current universe, like our Milky Way, the ratio between black hole and galaxy is so balanced and harmonious. But the story doesn't just stop at destruction. The universe has its own wonderful way of recycling. The amount of gas blown out by the black hole doesn't vanish into the void. It drifts into the space between galaxies, carrying heavy elements cooked in the reactors of stars. It enriches the intergalactic medium. Then, over time, this nutrient-rich gas stream falls back into other galaxies, or the old galaxy itself, to nourish new generations of stars. A great cycle. The black hole destroys to then create. Life and death in the universe are always intertwined like that. Previous computer simulations often failed when trying to recreate galaxy formation because they forgot the role of this black hole, foreman. They predicted too many large galaxies forming too early. Only when adding the black hole wind factor did everything match reality. Webb is helping us verify every detail of this process. It shows us how black holes sculpted the shape of galaxies over billions of years. But the black hole isn't the only one changing the face of the universe. There was a time the universe was submerged in thick darkness, a gloomy fog covering everything. Not a single ray of light could escape. That was the cosmic dark ages. How did the universe escape that darkness to become transparent and brilliant as today? Who cleared that fog? The answer lies in a silent war between light and darkness at the atomic level, and Webb is holding the key to this secret. Hello, are you guys still there? Don't worry, your screens aren't broken. This old man is showing you what the universe looked like about 380,000 years after the Big Bang. Welcome to the cosmic dark ages. After the Big Bang explosion, the universe was actually very bright, a hot plasma soup. But as the universe expanded, it cooled down. Lonely protons and electrons paired up to form neutral hydrogen atoms. The universe at this time became transparent, but at the same time, the lights went out completely. No stars were born yet. Darkness covered everything. But more scarily, space at this time was filled with neutral hydrogen gas. Imagine it like a thick fog, so thick that light could not penetrate. If you turned on a flashlight in this fog, the light would be swallowed immediately. The universe at this time was like a sealed room, lights off and full of smoke. So how did we get the clear, starry sky like today? Who cleaned up that fog? That process is called reionization. Then a miracle happened. The first stars ignited. They weren't gentle like our sun. They were giant monsters, blazing hot, emitting extremely strong ultraviolet UV rays. These UV rays were like blades of light, slashing into the hydrogen atoms in the fog, separating electrons from protons once again. This process turns neutral hydrogen opaque into ionized hydrogen transparent. Every primordial star was like an air purifier. It created a transparent bubble surrounding it. As more stars formed, these bubbles grew larger, touched each other, and merged. Finally, the entire fog was wiped out. The universe became crystal clear again. But the million-dollar question here is, exactly who did this? Was it the tiny primordial galaxies or the giant quasars? And did it happen fast or slow? To answer, James Webb looked back into the past. At the time, the universe was only about 1 billion years old, redshift from 6 to 10. The toughest problem is the escape fraction. Look at this paper lantern. Inside there is a candle, star, but the light is blocked by the paper layer, gas and dust of the galaxy itself, almost entirely. If primordial galaxies were also sealed tight like this, Then, no matter how many stars were inside, UV rays couldn't escape into space to clear the fog. But data from Webb brought extremely happy news. Webb discovered that primordial galaxies aren't like sealed lanterns. They are more like this bamboo basket. Webb's spectrum showed that galaxies back then had a very high escape fraction. They were full of holes, allowing ultraviolet photons to escape into intergalactic space easily. This overturns the old hypothesis that terrible energy sources, like quasars, were needed to clear the fog. No need. It was the normal galaxies, tiny but hardworking, with leaky light structures, that together made history. Their numerous quantity compensated for their small size. Many ants can fill a nest, and billions of small galaxies together lit up the universe. Webb also helps us redraw the timeline of this event. It didn't happen in a snap overnight. Data shows this process accelerated strongly around redshift 8, about 600 million years after the Big Bang. Before that, it was slow, but after this mark, the amount of fog, neutral hydrogen, disappeared very fast. By about 1 billion years after the Big Bang, the job was done. And it didn't happen evenly. The universe at that time was patchy, like a piece of Swiss cheese. Here, the fog had cleared because there were many galaxies gathering. There, it was still pitch dark. Webb is drawing a 3D map of this great cleanup process, showing it was more complex and chaotic than we thought. So we know who did it and when. But how can Webb see those tiny, faint galaxies from that ancient time to study? They are too far, too dim, even for a super telescope. The answer lies in a bonus gift from the genius Albert Einstein. The universe comes equipped with giant natural magnifying glasses, and Webb is using them in an extremely cunning way. What is that? Prepare your spirits, because in the final part, we will bend space and look at the sparkling fireflies from the primordial times. Do you see my handsome old face getting distorted through the bottom of this glass? That is physics. Light passing through a curved medium will be bent. Albert Einstein, that old man with the frizzy hair that everyone knows, said, "Space is not flat at all. If you place an extremely heavy object in the universe, it will dent space downwards, just like placing a bowling ball on a foam mattress. Light passing through that indentation will be bent." And here is the gift Einstein gave to James Webb: gravitational lensing. When Webb wants to look at a galaxy that is too far, too dim, it doesn't look alone. It turns its eyes toward a giant galaxy cluster sitting in the middle of the road. The gravity of this galaxy cluster acts exactly like the bottom of my glass. It bends the light from the object behind it, magnifying it 10, 50, or even 100 times. Shutterstock. In other words, the universe has prearranged giant natural telescopes floating out there. Webb just has to put its eye in the right spot. That is an astronomy cheat code. Thanks to the natural magnifying glass named Galaxy Cluster Abell-S 1063, Webb captured something beautiful. A galaxy stretched out into an arc shape, but sparkling inside it are points of light. Astronomers gave it a very poetic name: Firefly Sparkle. My friends, this firefly lived when the universe was only 600 million years old, meaning it had only lived 5% of its life. Normally, at that distance, a galaxy is just a blurry smear. But thanks to magnification, Webb saw its internal structure clear as day. And the surprise is, it isn't a solid block. It is a string of pearls consisting of 10 brilliant star clusters lined up together. This tells us the story of the birth of the Milky Way itself. This firefly galaxy is very light, only 1/10,000th the mass of the current Milky Way. It is an embryo. It proves that giant galaxies are not born huge. They are assembled gradually from smaller Lego blocks, which are exactly these star clusters. Furthermore, the star clusters in Firefly have different ages. This means stars are not born continuously. The galaxy eats gas, explodes to create stars in a burst, then rests due to black holes or radiation blowing the gas away, like I told you in part 2. Then eats again and explodes a new burst, like the heartbeat of the universe, beat by beat. But Webb doesn't just look at macro things, it also cares about the most important question: where do we come from? More specifically, where does water, the source of life, come from? Webb looked at dust disks orbiting young stars. Those are construction sites building new solar systems. There, Webb discovered crystalline water ice. Don't mistake this for ice in the fridge. In the cold universe, water usually freezes in an amorphous form, messy molecules. But crystalline ice, ordered, only forms under specific temperature conditions. Webb found this treasure trove of ice at the far edge of the dust disk, the freezer of the solar system. Why is this important? Because our Earth and rocky planets in general formed in the oven region near the Sun. At birth, Earth was scorching hot and dry as a piece of burnt toast. Water could not exist here. So where did our vast oceans come from? It had to be shipped in. Those chunks of crystalline ice that Webb saw at the far edge are the warehouse. Later, asteroids or comets, the shippers of the universe, would carry those ice chunks and crash into the inner rocky planets, bringing water and seeding life. Webb has confirmed that. The water reservoir was available right from the moment new stars formed. The ingredients for life are not rare. They wait everywhere in the universe, just waiting for a punctual shipper. We are going to talk about ICE, not ice in the fridge, but the ice that constructed the giants of the solar system and seeded life. Ready? Fasten your seatbelts. The ship is departing now. My brothers, look at Jupiter and Saturn, the two guardians of the solar system. Have you ever asked yourself why they are so fat and strapping, while our Earth is just like a marble next to a basketball? Scientists with big heads and nearsighted eyes, with computer models running purringly all day, have pointed out that the key lies in ice. Imagine it like this to make it easy to understand. Forming a giant gas planet is like you guys playing the snowball rolling game. To get a giant snowball, you need a sturdy core first. In the early universe, dust and gas flew around chaotically. In distant cold regions, water vapor froze into planetesimals. Let's just loosely call them boulders. They crashed into each other, stuck together, getting bigger. When this ice core was big enough, about a few dozen times the size of Earth, no joke, its gravity became insatiably greedy. It started sucking up all the surrounding hydrogen and helium gas clean. Whoosh! Like a glutton stumbling upon a free buffet, it swallowed the gas and puffed up into the Jupiters and Saturns of today. If there were no ice to act as the skeleton, the gas would just float around. No one could gather it. So, no ice, no giants. Simple as that. But old man Sengoku, how do you know what happened 4.6 billion years ago? Do you have Doraemon's time machine? No, I don't. But you humans have something fancier. The James Webb Space Telescope, JWST. Webb doesn't just see stars, it sees even the structure of ice in protoplanetary disks, the factories producing new planets. And this is when things get interesting. Webb discovered two types of ice. Amorphous ice forms when water vapor freezes extremely fast. Imagine you throw a bucket of water into liquid nitrogen. The water molecules panic and freeze messily, in no rows or order at all. Crystalline ice. This type is more aristocratic. It needs to freeze slowly or needs a warming period for water molecules to leisurely arrange themselves into orderly ranks. When Webb looked at the dust disk around a young star, looking exactly like the Sun when it was a teenager, it saw a lot of crystalline ice. What does this mean? It means the dust disk was once heated. Could be due to shock waves from collisions or radiation from the mother star. It's like finding an ice cube in the freezer, but its shape is distorted. You know immediately someone accidentally melted it, then froze it again. Ice in the universe is the diary recording the temperature history of an entire solar system. This is the part I like best. Webb didn't just find water ice, H2O. It also found a mobile bar in outer space with all sorts of other frozen ingredients. Carbon dioxide, CO2-dry ice, methane, CH4, ammonia, NH3. Sounds toxic, right? But oh my brothers, these are the raw materials of life. Imagine the universe is a great bartender. If this bartender scoops too little ice into the planet cup, we won't have gas giants. If he scoops too much ice, the material disk might shatter, creating a mess of planetary cores fighting for food. But most important is the mix. A planet forming from a pile of ice-rich material will have totally different chemical properties than a planet formed from dry rock. Webb is showing us that the cocktail recipe that created our solar system is not unique. It sees similar types of ice in all other protoplanetary disks. What does this mean? It means water, organic compounds, and atmospheres. Things necessary for you guys to sit here listening to this old man shoot the breeze are common. Rocky planets in the Goldilocks zone, habitable zone, not too hot, not too cold, in other star systems are perfectly capable of inheriting these frozen treasures. I bet my pipe that out there, second Earths are being kneaded from the same flour and yeast that the universe used to bake us. We aren't as special as we think. We are just one successful batch of cakes among countless other batches. And as Webb continues to catalog these ingredients, we will soon have the answer to the eternal question. Are aliens looking back at us and wondering why we have to go to work on Monday mornings? This old man just told you about the cold but promising beginning of planets. But the universe doesn't just have birth, it also has violent and magnificent deaths. Events releasing energy so terrible our tiny brains can hardly imagine. Webb doesn't just see the nursery, it also sees the graveyard of ancient stars. In the previous part, we talked about cosmic kindergartens, where planets are conceived in ice. But the universe is very balanced, my friends. If there is birth, there must be death. And the death of stars in the universe? Well, it isn't peaceful like a leaf falling. It is the most violent and magnificent firework display humanity has ever witnessed. Take a deep breath, because this part is going to be very explosive. I want you to imagine this. Grandpa's son of our house is a diligent employee. He works hard, shining regularly every day to feed us. And he plans to do so for his entire 10 billion year life. An exemplary worker. But Webb has just observed a totally different playboy guy. A gamma-ray burst, GRB. It lasted exactly 8 seconds. You didn't mishear. 8 seconds. Equal to the time it takes you to sneeze really hard once. But in those short 8 seconds, this guy released an amount of energy greater than the total energy the sun radiates in its entire 10 billion year life, combined. Imagine gathering all the salary you earn in 100 lifetimes, then burning it all in a snap of a finger to create the brightest fire in the world. That is how the universe plays big. This explosion shot matter out at a terrifying speed, 99.99% the speed of light. If it were a race car, just as you press the gas, you would already be on the other side of the galaxy. What is interesting? When the light of this explosion hit Webb's lens, the culprit had been dead for ages. This flash came from the dawn of the universe. It had to run a marathon for over 13 billion years to reach Earth, meaning we are watching an ancient documentary film. By the time Webb saw its afterglow, everything was history. But thanks to this time machine, we know how the first-generation stars died. Astronomers classify GRBS into two factions: the quick and dirty faction, under 2 seconds, usually due to two neutron stars, corpses of stars, crashing into each other. Boom, done. The long-haul faction, over 2 seconds. This is the death of a collapsing giant star. The 8-second explosion Webb caught belongs to the second faction. This is the final scream of a dying giant. So what happened to that ill-fated star? Let this old man explain in layman's terms. Imagine a star 20 times heavier than the sun. All its life it lives by burning nuclear fuel to resist the gravity that always wants to crush it inward. Like you using muscle power to hold up a ceiling that is collapsing. One day, the fuel runs out. Muscles are exhausted. Gravity wins. Crash. The entire core of the star collapses in an instant. It collapses so strongly, it forms a black hole. Now imagine this black hole like a brutal glutton lying in the middle of the star. Surrounding matter falls into its mouth violently, but it can't eat fast enough. Matter gets clogged at the throat, forming a wildly spinning disk, accretion disk. Magnetic fields twist like springs, and boom, it shoots out two extremely powerful jets perpendicular to the disk. These two jets are like two giant laser drills piercing through the shell of the collapsing star, blasting through the surface and rushing into the universe. Energy hot to billions of degrees. That is the moment the gamma ray flashes. It's like you squeezing a tube of toothpaste sealed at the top really hard, and the paste bursts out the sides at the speed of light. A horrific but magnificent scene. This is the most important part Webb achieved. It didn't just photograph the explosion, it used a spectrometer to smell what was in that explosion. And Webb smelled the scent of silicon, oxygen, and iron. Why does this make old man Sengoku get goosebumps? Because these elements, the oxygen you breathe, the iron in your blood, are formed in the nuclear reactor at the center of the star. When the star explodes, it throws all these precious things out into the universe. Webb is essentially looking into the internal organs of a star exposed to space. Finding iron and oxygen at an explosion from 13 billion years ago proves something extremely important. Even the first-generation stars in the early universe managed to manufacture heavy elements. Previously, scientists worried that stars back then were poor, low metal, so might die differently, not creating many heavy elements. But no, basic physics is exactly the same. Whether present or past, stars are still factories diligently manufacturing ingredients for life, then sacrificing themselves to scatter those ingredients everywhere. Your bodies, the phone you are holding, the cup of tea I am drinking, all are ashes of magnificent explosions like this from billions of years ago. We are children of the stars, quite literally. We just witnessed the death of a star and the birth of elements. But the story doesn't stop there. The light from this explosion on its 13 billion year marathon to Earth passed through many mysterious gas clouds. It's like shining a flashlight through fog. That light carries secrets about the dark ages of the universe, where light and darkness were playing tug of war. Webb used the very light of this death to illuminate the dark space between galaxies. In the previous part, we watched how a giant star blew its guts out. But in science, nothing is wasted. Even death has utility value. Astronomers, the most opportunistic people in the universe, utilize the very light from that explosion to make a flashlight illuminating the past. Let's walk on with this old man, the race back in time, and the wall of the dark ages. Imagine you are driving in a night of thick fog. You turn on the headlights, the light shines through the fog, and thanks to that, you know if the fog density is thick or thin, right? The gamma ray burst, GRB, I told you about in the previous part, is that extremely strong headlight. Its light had to travel through billions of light years of space to reach Earth. On the way, it passed through gas clouds scattered between galaxies. This is when magic happens. The intergalactic gas will eat a bit of the light. It leaves black lines in the spectrum, like barcodes on supermarket goods. By reading this barcode, astronomers know the composition and density of those gas clouds from billions of years ago. Specifically, Webb found traces of neutral hydrogen. This indicates the explosion happened during the ionization era. Sounds formidable, but put simply, in the old days, the universe was like a thick soup of fog, neutral hydrogen. Later, the first stars appeared, shone, and blew away that fog layer, making the universe transparent like today. Webb is using these lightning flashes to redraw the map to see where the fog had cleared and where it was still thick. It is redrawing the transparent history of the universe. But catching these explosions is very hard, my friends. They are like fickle rock stars, appearing brilliantly but disappearing extremely fast. On average, each galaxy only has one explosion in 1,000,000 years. As rare as hitting the jackpot. But because the universe is so wide, every day hundreds of explosions happen somewhere. The problem is how to know where it exploded to look. This is where teamwork reigns supreme. Ground telescopes play the role of watchmen. When they see a flash, they shout, "Hey Webb, 3 o'clock direction, trouble!" And Webb, no matter what it is busy observing, can pause to swivel sharply to that direction within minutes. Speed is life, because the afterglow of the explosion will fade extremely fast. If Webb is slow, like old man Sengoku, looking for reading glasses, then when it turns over, everything is already pitch black. Thanks to this flexibility, we have precious data about early deaths. Now, let's talk about another race equally thrilling, the race to find the farthest galaxy. Every few months you see the press making headlines. Webb found the farthest galaxy ever known. Then a few months later, record broken. It's like a Formula One race. Records are born to be broken. Currently, astronomers use a unit of measurement called redshift shutterstock. Simple explanation. When an ambulance runs away from you, the siren pitch lowers, wavelength lengthens. Light is the same. When the universe expands, galaxies run away from us. Their light is stretched out and turns red. Bigger number arrow, redder arrow, farther arrow, more ancient. Webb's JADES project found a galaxy at redshift 14, about 290 million years after the Big Bang. Then there was a candidate at level 16, only 250 million years after the Big Bang. Why does the record keep increasing? Webb gets better with use. Astronomers understand this machine better day by day, knowing how to filter noise, knowing how to look deeper. AI support. Computer algorithms, machine learning, now scan images sharper than human eyes. They find faint spots we missed. Probability. The wider the sky area you search, the easier it is to catch rare monsters. But does this race have a stop? It does, my friends. We cannot look back to infinity. There will be a time we hit the dark ages. That is the time before the first star was born. Before redshift about 20, the universe was full of darkness and cold gas. No stars, no galaxies. What would Webb take pictures of? At that time, Webb might see the faint light of hydrogen gas, but will no longer find any galaxies. Currently, we are at level 14 to 16. The distance to level 20 is shrinking. Webb is extending humanity's vision to cover 98% of cosmic history. We are standing at the edge of understanding, looking into the abyss where everything began. These record-holding galaxies aren't just numbers to brag about. They are freaks, in a good sense. They are brighter, bigger, and matured earlier than computer models predicted. This makes theorists tear their hair out. Why is it so big and strapping right after being born? Precisely those absurdities are the interesting things. It forces us to rewrite textbooks. The universe is complex and precocious far beyond what we thought. We have seen the beginning, seen the death, and seen the border of time. But behind all those movements, there is a mysterious force controlling the game. An invisible force tearing the universe apart, pushing galaxies away from each other faster. Scientists call it dark energy. But what the hell is it really? And will it tear apart even the atoms in our bodies one day? Webb is helping us answer that scary question. In the previous parts, we talked about birth, ice, death, explosions, and the past, ancient light. Now I want to invite you to look at something scarier, more mysterious, and it determines the fate of us all, the future. Hold tight to the handrail because we are about to face the biggest phantom of the universe. Do you guys remember middle school physics? If you throw a ball up into the sky, gravity will slow it down, and then it falls. The universe is the same. After the Big Bang, all matter flew apart. Logically, the gravity of galaxies should pull them back, making the universe expand slower. But no. In the late 90s, astronomers dropped their jaws when discovering the universe is expanding faster. Like the ball you threw up, instead of falling, it suddenly attached a rocket engine and flew away out of sight. Who is the culprit? We call it dark energy. Called dark because we are totally blind to it. We don't see it, can't touch it, but it makes up about 70% of the universe. It is like an invisible force pushing space apart from the inside. Webb stepped in to check the file of this criminal. By measuring distant supernovae, Webb confirmed that dark energy has been running wild for billions of years. It is a constant, sullen, and steadfast, always pushing galaxies away from each other. So how will the tug of war between gravity, pulling in, and dark energy, pushing out, end? Based on Webb's data, this old man has 3 scenarios for you. Don't lose sleep after hearing them. Scenario 1, Big Crunch. If dark energy gets weaker, like running out of gas, gravity will win. The universe will stop expanding and start shrinking. Everything will crash into each other, heat up terribly, and end at a single compressed point. Boom, maybe a new Big Bang will start again. Sad news, current data shows this probability is very low. Scenario 2, Big Rip. If dark energy gets stronger over time, it will go crazy. First, it tears galaxies apart. Then, it tears star systems apart. Finally, the repulsive force is so strong, it tears apart even the atoms in your body. All matter in the universe gets torn into lonely elementary particles. A rather painful ending. Scenario 3, the Big Freeze, highest probability. If dark energy is a constant, as Webb is seeing, the universe will expand forever. Galaxies will drift so far that their light never reaches each other again. The night sky will become pitch black. Stars will burn out of fuel and fade out. The universe will become a vast, cold, dark, and permanently empty place. Sounds sad, right? But don't worry, this won't happen for billions of years. By then, humanity might have moved house to another universe already. Although Webb is the strongest god-eye in history, this old man must confess to you. Webb has limits too. Webb is like an excellent sniper, but its range only reaches redshift 20, about 200 million years after the Big Bang. Farther than that? That is the murky dark zone. Galaxies then were too small, too dim, and light was stretched too much, into far infrared or radio that Webb can't see. So what is after Webb? Scientists are incubating new monsters. On the ground, giant telescopes with mirrors as big as stadiums, using adaptive optics technology to blur out atmospheric turbulence. In space, future generations of telescopes will hunt for the first stars, Pop-3 stars, the ancestors of all light. But that is a story for a few decades from now. For now, Webb is still king. My friends, we are living in the golden age of astronomy. Never before has humanity seen the universe so clearly and profoundly. We have seen the factory producing life from ice. We have witnessed the internal organs of dead stars. We have seen newborn galaxies breaking every rule of physics. The universe turns out to be vaster, stranger, and more magnificent than any wild dream of humans. Every photo Webb sends back is a humble reminder that we are tiny, but our intellect and curiosity reach to the very end of time. The story of the universe has waited 13.8 billion years to be told. And we, small creatures on this blue rock, are the first to hear it fully. The journey of discovery isn't over. It has just begun. Keep your eyes always pointing up at the sky. I am Sengoku. Thank you for visiting Black True. Don't forget to like, share, and subscribe, so this old man has the motivation to continue telling cosmic secrets next time. Now I'm going to brew another pot of tea. Goodbye, travelers.